Stand beneath a moonless sky and you will feel it, the hush that seems to hold the stars in place. Nothing moves to the naked eye. Constellations sit like stitching on a great black sail. Yet when we pass their light through instruments that do not blink, that quiet sky begins to shout. The thin rainbow of a galaxy does not line up where it should. Its stripes slide toward red, a sign that the waves we receive have been stretched in flight. The farther the galaxy, the greater the slide. The image says stillness. The measurement says motion. Two truths, both persuasive, both at odds. Where do we stand when looking and listening disagree? A single photograph deepens the confusion. A telescope was told to stare not at a famous nebula, but at a patch of darkness no bigger than a grain of sand held at arm's length. It waited, patient as a lighthouse, stacking faint photons that arrived one by one. What looked empty filled with thousands of small islands, each a city of stars. The vision is serene, like a winter harbor before dawn, but the spectra taken of such islands tell us they are retreating, and their retreat follows a rule. Speed grows with distance. The farther we look, the faster the backstep. How can a harbor be calm while every ship drifts outward? We begin with a paradox because paradox is a compass. If the sky is truly static, then a mechanism must hold every star as if pinned to a board. If the sky is not static, if the fabric itself grows, then the calm is an illusion born of scale and patience. Which picture survives when we force it to face the data? If growth is real, what set it in motion? If there was a first fire, what remains of it after billions of years of cooling? A clue must still exist, not in one place, but everywhere at once. Look with your ears. A radio dish, turned from the earth. Here's a gentle hiss that arrives from all directions. We subtract the warmth of the ground and the glare of the sun. The hush remains, nearly the same no matter where the dish points. It is not the sound of wind in the trees. It is not the chatter of distant stations. It is the room tone of the universe, a faint bath of microwaves that wraps the entire sky. Even if you point at a cold patch of space between stars, it is there, stubborn and even, a soundless choir that cannot be silenced. What kind of room keeps its tone for so long? Light teaches by changing. A short wave carries more energy than a long one. As space grows, every crest and valley is pulled apart, so light on the road becomes redder by the time it reaches us. Blue leaves, red arrives. From a young fog of fire, a blue-white glow sets off. Then time and growth turn it into a cool whisper. This whisper, spread across the sky, is a veil more than a beam. A veil woven from ancient photons that have not bumped into matter since the cosmos was very young. Lay an antenna against that veil, and you can touch the past without leaving your hill. We need the human scale to keep our sense. Think of an escalator in a quiet mall at night. You stand without walking. The steps carry you anyway. People scattered along the escalator separate as the machine moves. None of them needs to break into a run. The distance grows because the floor itself is in motion. In plain terms, galaxies can drift apart because space changes between them, not because each one fires an engine against a fixed backdrop. A universe that never changes demands a perfect balancing act, a constant push that holds everything in place against all pulls. One grain of error, one tilt, and the balance would fail. We find no evidence for such a perfect governor. We do find that color shifts scale with distance, a simple rule that is most elegant when space itself grows. We do find the sky, wide veil of microwave hiss, a remnant that fits a story of early heat cooling over time. The picture of a still theater full of frozen actors cannot withstand these tests. There are two ways to approach this. From the far horizon and from the surrounding air. The far horizon comes from mapping the colors of galaxies and linking those colors to distance. The surrounding air comes from reading the soft hiss that wraps the sky and measuring its tiny patchwork of warm and cool spots. These routes were built by different tools, and cared for by different kinds of patients. Yet they meet in the same valley. Early time was dense and hot. Later time is thin and cool. Structure rose from small ripples that were present before any star burned. The sky is not a poster. It is a diary that cooled slowly and kept its handwriting. A hard question waits at the threshold. Could there be a birth without a boundary? If we trace the growth backward, do we reach a point where our math writes down infinities and then falls silent? That linguistic edge does not force a final meaning. It invites more careful language and more stubborn measurement. Some teams sketch a brief and violent smoothing in the earliest fraction of a second. Others imagine that before growth there was compression, and that our beginning was a rebound. We do not settle those ideas by taste. We ask the veil. Which one of these leaves the right pattern of tiny spots? And which one predicts a relation between distance and color that matches our maps? Let the veil teach us one more secret. It is almost equal in all directions. But the almost matters. The tiny unevenness is not random. It is structured. Slightly denser patches correspond to places where gravity would later form galaxies. Slightly emptier patches correspond to great voids, the silent spaces between walls of light. When we read the statistics of those patches, we recover the birth rhythms of the cosmic fluid. It is as if we have a photograph of a child in the womb and can measure the heartbeat that set the tempo for a lifetime. The veil cannot tell us whether a purpose lies behind the heat, but it can describe the grammar by which chaos grew into order. Once a paradox starts to straighten, new questions rise. If space stretches, where is the center? That question carries a hidden assumption that there must be an outside into which the inside grows. Instead, imagine that there is no surrounding room, only the floor itself, and that every tile moves from its neighbors in the same way. Stand anywhere and draw a circle. Wait, and the circle grows evenly. No point is privileged. The idea offends our habit of giving every story a special seat, but the sky does not share our habits. It offers a rule instead of a throne. We also face the seduction of the singular point, the place where equations hint at a breakdown. A breakdown in math may mark a boundary in nature, or it may only mark the edge of our current map. We refuse to promote a hint to a law. We learn by asking whether a proposal leaves fingerprints on the veil, or in the arrangement of galaxies, or in the variation of brightness for objects that we can treat as standard lights. A strong idea survives many kinds of measurement. A weak one needs special pleading, and the sky has no patience for special pleading. Consider ordinary life. A kettle that has cooled does not warm itself without fuel. A car that slows on a hill does not speed up without a push. If the universe today shows growth that speeds up, then some agent acts like fuel on the largest scales. We do not see it. We infer it from the way distant lights fade and from how the veil's statistics align with those fades. If this agent is a real field, it might be constant in strength, or it might change over time. The sky will have the final word. Our job is to test, not to announce. Doubt is part of discipline. What if the color shifts were not about growth at all, but about light losing energy on long journeys in some subtle way? That notion falls when we check the details. The shifts follow a clean relation with distance that matches a changing floor better than a tired light. The veil's statistics also match the growth story and resist the tired light story. When two independent lines of evidence converge, the burden of proof shifts. The still sky becomes the special case that needs rescue, and the growing sky becomes the simple case that needs only accuracy. We must also face our own hunger for meaning that reaches beyond what the signals can bear. We may want a first cause, stated in a single sentence. We may want a guarantee that minds like ours were meant to arise. The evidence does not answer such questions. That is not a failure. It is a freedom. We can describe the road that turns heat into structure. We can measure how fast the road stretches now. We can compare different guesses about the early rhythm, and we can say which ones fit and which ones do not. We can protect the right to say we do not know, and we can promise to keep asking in ways the sky can judge. Let us return to the night and its two teachers. The deep photograph, serene and dense with faint galaxies, offers the feeling of a cathedral. The split light, its colored stripes shifting as distance grows, offers the cadence of a law. The radio hiss, present in all directions, offers the fact of a common past. The tiny modeling on that hiss offers the seeds from which everything we can point to later grew. Each teacher speaks in a different voice. Together they tell one story. The stage itself is moving. Actors ride the stage. The script is written in statistics that can be checked by other hands on other hills. If there was a beginning, it will not be found in a single bright spark. It will be found in consistency. In how many lines of data point to the same pattern. In how few special tricks are needed to make the numbers agree. That is how we turn paradox into map. That is how we move from a still picture to a living record. We keep our words small and our patience long. We let the sky correct us. We accept that meaning, if there is any beyond the physical, cannot be extracted by force from a graph. The hook is set. The eye sees calm. The instrument hears flight. The veil carries a memory of heat and of tiny ripples that are the ancestors of every star and every shoreline. This is where our story truly begins, with a contradiction that refuses to be ignored, and with tools that are honest even when they bring bad news to our instincts. We will follow those tools. We will let them lead through theories that try to arrest growth, through maps that tie color to distance, through proposals that treat the early universe as a seed, and through the reading of the oldest light written on the sky. Support evidence. First, storytelling. Like and subscribe to the Quiet Universe channel. We start by testing the constant that tried to freeze the cosmos. Then we watch why it could not hold. At the start of the 20th century, the universe was supposed to be still. The stars, it was said, floated in a vast, eternal ocean of black. If gravity was always pulling, then some quiet force must be pushing back, something that balanced every attraction so that the cosmos would not collapse. That balance, beautiful in its simplicity, rested on an assumption the universe had always been there. No growth, no decay, just an unchanging stage where celestial bodies performed slow and endless motions. It was a comforting picture. It was also wrong. The story begins with equations, not telescopes. A young theorist tried to describe how gravity curves space itself, how mass tells the geometry of the universe how to bend. The math worked too well. It showed that gravity could not rest. A static universe would crumble under its own weight, or it would explode outward. So he added a small term, a quiet adjustment, a symbol that would hold everything still. He called it a constant, a pressure that countered gravity exactly, neither creating nor destroying motion. The number had no origin, no reason, just a task to preserve the eternal night. For a time, the constant worked, at least on paper. The universe could now exist in equilibrium, a perfect architecture that did not expand or collapse. But perfection in nature is brittle. The smallest disturbance would make it fail. A nudge here, a fluctuation there, and the cosmic stage would begin to breathe, first imperceptibly, then in runaway motion. In plain terms, what seemed like stability was really a coin balanced on its edge. The lightest touch could send it rolling. Imagine building a dam across a great river. You calculate the strength of the walls, the pressure of the water, the structure of the valley. You add a single plank, too many, and the water level rises by a hair. The new pressure pushes harder against the dam. It bows, it groans, it cracks. The balance breaks. Not because the materials are bad, but because the idea of perfect balance was never real to begin with. The constant was that extra plank, beautiful, precise, and doomed to fail. Observers began to notice hints that something was not matching the picture. The motion of distant star clusters did not obey the script of a static cosmos. Through narrow tubes of glass, faint smears of light showed odd behaviors. Their spectral lines shifted toward red, as if they were running away. At first, this seemed like error. Instruments trembled. Glass expanded with temperature. Data could lie. Yet the pattern repeated across many directions, many nights, many hands. The evidence was patient. It waited for us to listen. If the galaxies were indeed retreating, then the constant was no safeguard. It was a mirage. Gravity still pulled, but nothing pushed back in the right way. The fabric itself was not sitting still. It was stretching. When space stretches, every distant beacon carries the news in its light. The further the beacon, the more the stretch. The message is written not in words but in color. Each photon leaves home with a fixed wavelength. When it reaches us, the wave is longer. The energy has not vanished. It has been shared with the expanding stage that carries it. Think again of that dam. Once the water finds a crack, it does not stop. It widens the gap and floods the valley. Space behaves the same. Once the constant loses its grip, the tiniest nudge grows. Expansion feeds on itself. Distances double, then double again. The dam breaks, and the river becomes the world. For the man who invented the constant, the discovery was painful. He had introduced it to avoid instability, to protect the dream of eternity. When the evidence of expansion arrived, he called the constant his greatest blunder. Yet history is never so simple. The same constant would return decades later, in another context, under another name, to describe something even stranger, the acceleration of the cosmos. What was once a patch became a prophecy. Why does this matter? Because it shows that even the most elegant fix can blind us when it fits too perfectly. The constant was not born of measurement, but of preference. It was a human wish, written into the equations to keep the universe comfortable. When reality refused comfort, the wish had to go. The lesson is not about one equation, but about how science grows. It does not punish mistakes, it punishes stubbornness. From a human scale, this story feels familiar. We balance our lives on constants of our own making, numbers that promise equilibrium. A city plans its traffic for the year, not for a century. A company predicts growth as if the market were static. A heart believes its rhythm will stay steady. Yet in each case, small shifts accumulate. Equilibrium gives way to motion. The rule is universal. Nothing perfectly holds. If the cosmos could not stay fixed, then its story must include a beginning. A constant that would not hold forces us to imagine a time before the balance existed. That thought is both liberating and terrifying. It means the universe has a history. It means change is not noise, but nature. The equations can now tell tales of birth, of growth, of cooling, of structure. They are no longer frozen diagrams, they are chronicles. Some resisted. To abandon the constant was to admit that the sky itself evolves, that the heavens are not immune to time. Philosophers and priests had long declared the stars eternal. Now, glass and prism said otherwise. The arguments were fierce. The data did not flinch. Color shifts, once dismissed as technical error, became the grammar of expansion. The constant, once hailed as balance, became a symbol of denial. In everyday language, what happened here was the triumph of humility over desire. Nature had no reason to respect our idea of stillness. It preferred motion. The light from galaxies wrote its verdict across space. The constant was not destroyed by theory. It was undone by observation. Still, the idea left a trace. Later generations would revisit the same symbol, not to freeze the cosmos, but to explain why the expansion is speeding up. The constant that would not hold was reborn as dark energy, the new name for a similar pressure that drives the widening of space today. The dam failed, but the river still carries its ghost. We see it in the data, we test it in the redshift of supernova, and we build new equations around the echo of an old mistake. Why it matters is clear. Each failed fix reveals a deeper rule. The sky does not promise comfort, it promises coherence. Our task is to let go of the constants that only please us, and hold on to the ones that survive measurement. In the balance between desire and evidence, evidence wins slowly, but it wins. Now imagine standing on a mountain with a small telescope, tracing the faint smear of a nearby galaxy. You record its color, you calculate its speed, you compare the result with others across the sky. The pattern emerges, steady and unyielding. No constant can flatten it. The universe is moving, and the motion obeys a simple law: the farther, the faster. The stillness of the night is an illusion born of short lifetimes and slow eyes. The constant that would not hold is not just a number in an equation, it is a warning written in light. Every time we cling to a perfect balance, nature shifts beneath our feet. Every time we fix a number to preserve peace, the data remind us that peace was never the goal. The goal is truth, and truth breathes. The first act of the universe we can measure is motion. From that motion comes the question: if the constant could not keep the cosmos still, what else did it fail to hide? We turn next to the maps of color and distance, where galaxies themselves will reveal the true rhythm of expansion. A quiet revolution began in the dark of observatories. Through narrow slits of glass, light from distant smudges on the sky was stretched into rainbows. On those rainbows, thin dark lines cut across the colors. Each line marked a specific chemical note, an element singing the same tune it would sing in a laboratory flame. The question was simple but daring: are those tunes shifted from where they should be? And if so, why? The answer would redraw the scale of the cosmos. At first, the work was slow and fragile. Each spectrum took hours of exposure. Each photographic plate carried its own scars. When a few galaxies showed small shifts toward red, some blamed the instruments. Temperature changes could warp the glass. A misaligned prism could smear the pattern. But as more and more plates came out of the darkroom, a pattern began to repeat. The shift was not random. It grew larger for fainter galaxies, smaller for bright ones. The farther the light, the more it had been stretched on the way. The signal was consistent, and consistency is how nature speaks. One galaxy stood out: the Andromeda spiral. Through a small telescope, it looks like a faint blur, yet it covers more sky than the full moon. Its light was found to shift in the opposite direction, toward blue. That meant it was coming closer, not receding. A strange twist, because nearly every other smudge on the plates was redshifted. In plain terms, Andromeda was the exception that proved the rule. Our neighbor moves toward us because of local gravity, but the background of galaxies shows a universal drift away. The pattern does not depend on who looks or where. Imagine a city map printed on rubber. If the rubber stretches evenly, all streets grow longer, and the distance between intersections increases. If you are standing at one corner, you see every other corner move away. The closer ones drift slowly, the distant ones faster. The map does not stretch into an empty room. It stretches itself. In everyday language, galaxies are not flying through space like bullets in air. The air itself is expanding, and the galaxies ride on it. As more observations came in, the relationship between distance and redshift solidified into a rule. Plot the velocity inferred from the color shift against the distance inferred from the brightness of standard lights, and a straight line appears. The slope of that line is the cosmic rate of expansion. The faster the slope, the younger the universe would have to be if we rewound it. The slower the slope, the older the world. The simplicity was striking, almost suspicious. How could the chaos of countless galaxies follow one clean rule? But the data were stubborn. The rule held. The real challenge was measuring distance. Light weakens with the square of the distance, but galaxies vary in size and brightness. A dim galaxy, it could be far or simply small. The breakthrough came from a class of stars that pulse in a predictable rhythm. Measure the period of their flicker, and you know their true brightness. Compare that with how bright they appear, and you know their distance. These pulsing stars became the yardsticks of the universe. Using them, astronomers built a ladder from nearby clusters to faraway smears. The redshift law transformed from curiosity to evidence. Once we saw that every patch of sky obeys the same slope, the picture changed. There was no privileged center. Every observer, wherever they stand, would see the same pattern of flight. This is the deep symmetry of the universe. No throne, no hub, no edge. A humbling symmetry that pulls the human ego out by the roots. We live not at the center, but inside and everywhere that grows. The numbers themselves told a story of scale we could barely imagine. The distances involved were millions, then billions of light years. Each light year is nearly 10 trillion kilometers. Yet we toss the word casually, as if human language could hold it. The light from a distant galaxy began its trip when Earth was still a newborn crust. By the time it arrived, whole continents had drifted, mountains had risen, and species had come and gone. To look through the telescope is to look backward in time. In plain terms, redshift is a time machine. When we see a galaxy whose light has been stretched twice its original wavelength, we are seeing it as it was when the universe was half its present size. No spaceship could take us there. Space itself has carried the message. The more we map, the deeper we see into history. The telescope does not just collect photons, it collects years, decades, epochs, until our own age is just the thin outer layer of a vast onion of time. The first complete map was chaotic but thrilling. Clusters of galaxies formed filaments, long chains strung across emptiness. Between them lay enormous voids, regions where little light could be found. The universe looked less like a smooth fog and more like a vast web. The redshift data revealed the pattern in 3 dimensions: dense walls, empty tunnels, intersections where superclusters sit like knots. The cosmos was not only expanding, it was also structured. The structure itself was fossilized motion. Why does this matter? Because the redshift map is the first mirror large enough to reflect the universe back at us. It shows not only how far we can see, but how we fit inside something that has no edge. It tells us that motion and distance are linked by geometry, not by accident. It confirms that our instruments, humble as they are, can read the signature of creation written in light that has traveled for billions of years. The human scale analogy helps. Imagine watching a train depart in slow motion. Each carriage is farther from you than the one before. The sound of its whistle drops in pitch as it recedes. Light behaves like that whistle. Except the distances are cosmic, and the shift is in color, not sound. We read the fading tone of the universe with prisms and patience. Some questioned whether the redshift could have another cause. Perhaps the light loses energy by some unknown interaction on the way. Perhaps dust steals energy in subtle ways. Tests were made. The pattern of shifts matched distance too neatly to be random loss. The energy of light is not drained like a battery. It is diluted because space itself stretches. We tested in many directions, with many wavelengths, and the slope stayed the same. Random decay would not know how to keep that rule. Still, the data came with tension. Early estimates of distance and velocity made the universe appear younger than some stars within it, an absurd contradiction. That meant the slope, the expansion rate, was not yet right. Instruments were crude. The distance ladder wobbled. Each correction brought the numbers closer to sanity. The process was not a failure. It was refinement. In science, doubt is not the opposite of belief. It is the tool that sharpens belief. At its core, redshift mapping turned the heavens into a measurable phenomenon. No longer eternal lights pinned to a dome, but moving participants in a common unfolding. Each spectrum a line of the script, each telescope a reader of those lines. The galaxies do not whisper, they chant in harmony. The red tones, stretched and cooled, are the language of growth. From this perspective, even Andromeda's blue shift becomes a clue. It tells us that local gravity can outweigh expansion on small scales. Within our neighborhood, attraction wins. Over cosmic scales, expansion does. The universe is not one story but a hierarchy of stories, each with its own rhythm. Planets orbit stars, stars orbit galaxies. Galaxies themselves drift on the moving fabric of space. When we add all these threads together, a new image emerges. The cosmos is not a collection of objects moving through void. It is a single fabric changing its own measure of distance. The Redshift map is our first reliable chart of that change. It stretches across the sky like a new kind of atlas, one that measures time and speed with color instead of ink. Why it matters again is that this map transforms our relationship with scale. We are not tiny dots lost in infinity. We are points within a story that can be measured, tested, revised, and understood. We have turned the oldest light into evidence, the faintest signal into geometry. The universe is no longer beyond comprehension. It is vast, yes, but it is readable. The rule discovered in those spectra opened a gate for new physics. It told us that expansion is real, but it did not tell us why. To find the cause of the motion, we must trace the light back further, beyond galaxies, beyond stars, to an age when the universe was young and hot enough for light itself to be trapped in matter. The Redshift map gives direction. The next evidence lies in a glow that fills the sky with invisible fire. We follow that glow next, toward the first vision of a primeval atom, and the mind that dared to propose it. Long before the discovery of microwaves humming through space, a quiet mind in a black robe looked at the same evidence and saw a story no one else was ready to tell. He was both a priest and a physicist, fluent in the language of scripture and in the mathematics of relativity. To him, the universe did not need to be static, and it did not need eternal balance. It could evolve. It could grow. It could have been born. He studied the equations that had been patched with the constant of stillness and saw that, without the patch, the math naturally described motion. The universe, if left to itself, would expand or contract depending on its energy content. What if, he wondered, we are catching it in the middle of its life cycle? What if time had a beginning that physics could describe? He was careful, but his idea was radical. He called it the hypothesis of the primeval atom. Imagine, he said, all matter and energy condensed into a single point, not a stone, not a sphere, but a state beyond current imagination. From that point, the entire cosmos expanded, not into space, but into existence itself. The idea was shocking. It had the flavor of creation, but it arose not from theology, rather from the same equations that explained gravity and light. The proposal was not an answer to why the universe exists, but to how it unfolds. In everyday language, he imagined the cosmos as a firework frozen in its earliest instant. Every particle, every field, every trace of what would become galaxies and dust. And life was once packed in a density beyond experiment. When the firework burst, space itself expanded, carrying everything outward. The light that left in those first moments has been stretching ever since. This was not mysticism. It was the simplest consequence of the new physics. The response from the scientific world was swift and harsh. Many saw his theory as a step backward, a surrender to myth dressed in equations. Some mocked it with a new name, a casual insult that would later become history's headline, the Big Bang. The term was meant to dismiss, not to describe, yet the priest accepted it quietly, because names do not decide truth. Evidence does. He turned his attention to what evidence could exist if the universe had once been hot and dense. A young universe, expanding and cooling, would leave behind fossils of that state. There would be a faint afterglow, a remnant heat filling all space, invisible but measurable. There would be a pattern in the arrangement of galaxies, traces of the first clumps of matter, and there would be a curve in the relation between distance and velocity. a sign that expansion had changed speed over time. Each of these could, in principle, be tested for decades. The idea drifted between acceptance and doubt. Observers collected more redshift data. Theorists refined models of matter and radiation. And yet the evidence for an origin older than any star remained elusive. People preferred an eternal cosmos that required no birth. The steady-state picture seemed safer. Even comforting new matter could appear as space expanded, keeping the average density constant forever. No beginning, no end, no singularity, just an eternal balance. The priest's model challenged that comfort. It said there was a start, a time when space and matter were the same thing, when even light could not escape the crowd. The thought was disquieting. It removed the luxury of eternal repetition. A beginning means change, and change invites purpose, even if none exists. Science tries to avoid questions of purpose, but humans rarely can. Still, one does not need belief to respect a good prediction. If the primeval atom was real, its heat should still echo today, though vastly cooled. The universe should be filled with radiation of a specific temperature, not too hot to burn, not too cold to hide, roughly a few degrees above absolute zero. He wrote it down, not as revelation, but as a calculation. No one had yet built the right instruments to search for it. Think of a stone thrown into a pond. Long after the stone sinks, ripples still reach the shore. The ripples carry the memory of the impact. Even though the stone is gone, in the same way, the radiation of the early universe carries the memory of the first expansion, even though the conditions that created it have vanished. The pond has grown vast, but the ripple persists. Why does this matter? Because the priest's imagination set a test that no philosophical argument could dodge. If the glow exists, it can be measured. If it does not, the theory falls. In science, that is the highest form of honesty. He understood that truth must be falsifiable, that beauty and faith, while comforting, are not evidence. For years, the community chose to ignore the idea, not out of malice, but inertia. Observations focused on galaxies, not on background radiation. The tools for detecting microwaves with high sensitivity did not yet exist. The idea of a cosmic afterglow lingered in journals, waiting for technology to catch up. When the right antennas were finally built, the discovery came by accident, from radio engineers chasing noise rather than cosmologists chasing truth. In hindsight, the priest had pointed to the fingerprints of the early universe long before anyone saw them. The radiation he predicted became the most powerful piece of evidence that the cosmos was once young and hot. The irony is elegant. The man who was accused of mixing religion with science had given science one of its most testable cosmic origins. At its heart, the hypothesis of the primeval atom is not about faith. It is about the courage to follow equations beyond habit. It says that even a universe that seems eternal can have a traceable history. It says that the laws of physics can run backward until they approach a limit where new laws are needed. That is not an act of devotion. It is an act of curiosity. On a human scale, his story reminds us that conviction and humility can coexist. He believed deeply in a creator, but he also believed that the creator's work should be open to examination. To test the divine is, in a way, to honor it. For only false gods fear scrutiny. He wore his collar while lecturing on relativity and carried his chalk like a candle. His faith did not dull his science, it sharpened his sense of wonder. Some still resist the idea of a cosmic beginning, pointing out that a singular point cannot be observed, that our laws break before reaching it. They are right. The primeval atom is not a literal ball of matter. It is a metaphor for a state where all known physics converges and then fails. That failure is not defeat. It is invitation. The next generations would turn that invitation into new physics, into ideas of inflation, quantum foam, and the birth of time itself. The priest's legacy lives not only in the theory but in the example it set. To let data correct belief, to let calculation shape awe, to speak in both equations and metaphors without confusing them. His primeval atom was the seed of modern cosmology. Every measurement of cosmic background, every map of structure, every simulation of early expansion traces its ancestry to that seed. Why it matters once more is that it shows the power of an idea to outlive its author. The man passed away before the glow was measured, but his equation survived. When the radiation was found, the world quietly rewrote the footnotes. What began as heresy became the standard model. The universe had a beginning, and its echo was everywhere. Now the stage is set for the next revelation. The predicted afterglow has been found, and its uniformity and faint variations will tell us not only that the primeval atom existed, but how it evolved. We turn next to that faint sky-wide glow, the oldest light ever seen, and the story it still tells. The discovery began with confusion. Two engineers tuning a large radio antenna in a quiet field kept hearing a hiss that refused to fade. They turned the dish toward different parts of the sky, wiped away pigeon droppings, checked cables, replaced amplifiers, even listened at night when the air was still. The hiss was constant. It came from everywhere and did not change with the hour. What they had found was not noise. It was a voice that had waited for billions of years to be heard. This faint radiation filled every corner of the sky with near-perfect uniformity, a background glow that came from no particular direction. Its temperature was just under 3 degrees above absolute zero. It matched the prediction of the priest's primeval atom theory with eerie precision. The universe, once a furnace of plasma and light, had cooled until atoms could form and photons could finally travel free. Those photons are what the engineers detected. They are the oldest light, still crossing space, still recording the moment when matter and radiation first parted ways. Imagine standing in a vast hall after a great concert. The instruments are gone. The stage is empty, but the echo lingers in the rafters. That echo is the cosmic microwave background. It is the aftersound of creation, not loud but everywhere. Each photon is a messenger that has never collided since it left the crowd of early atoms. When we capture them with sensitive detectors, we are catching the leftover shimmer of a universe that was once as bright and dense as the surface of a star. In plain terms, this light is a fossil. It comes from a time about 380,000 years after the universe began, when the hot fog thinned enough for light to move freely. Before that, the cosmos was opaque, like the interior of a cloud. After that, transparency ruled. Every patch of space emitted light of nearly the same color, a soft orange that stretched into microwaves as space expanded. The radiation fills the sky with the same temperature to 1 part in 100,000. Yet within that perfection lie tiny ripples that changed everything. Those ripples are the fingerprints of structure. Slightly denser regions in the early universe trapped gravity more strongly, while slightly thinner regions expanded faster. These differences were small, but they grew. Over billions of years, they became galaxies, clusters, and cosmic filaments. When we map the ripples in the background light, we are reading the blueprint of every large-scale feature we see today. The sky itself is a photograph of the universe's youth. Detecting those ripples required instruments far more precise than the first antennas. Satellites were launched above the atmosphere to scan the sky in microwaves. Free from the noise of Earth, they mapped the temperature variations with exquisite accuracy, painting a sky speckled with cold and warm spots. The map was astonishingly detailed, revealing a pattern of harmonics, like the vibrations of a cosmic drum. Each peak and trough told of the density of matter, the amount of ordinary atoms, dark matter, and radiation in the early universe. The meaning was profound. The data confirmed that the universe is flat on large scales, that its geometry follows the simplest rules of Euclidean space. It showed that matter and radiation were once coupled in a hot plasma that vibrated like sound waves through air. These primordial sound waves left their imprint on the light we see today. When scientists speak of reading the music of the cosmos, they are not using poetry. They are reading literal harmonics frozen into the oldest light. Why does this matter? Because the cosmic background is the most direct evidence we have of our own beginnings. It is not an inference, it is observation. Every direction holds the same story. The near-perfect uniformity proves that the cosmos was once in thermal contact. The tiny irregularities explain why it did not remain featureless. The universe is a balance between smoothness and grain, between calm and potential. Without those minute differences, nothing would have formed. We would have lived in an endless fog of hydrogen. In everyday language, the background light is a baby picture. It shows the universe as it was long before any star was born. The red patches are slightly warmer, the blue patches slightly cooler. The contrast is less than 0.1%. Yet those small differences define everything that followed. A few microkelvins decided where galaxies would form and where voids would grow. From those tiny seeds, complexity arose. When we translate the map into numbers, we can measure the age of the universe with astonishing precision. The ratios of peaks in the power spectrum tell us how much matter, how much radiation, and how much mysterious energy drives expansion. The background light is not just a photograph. It is a census. It reveals that most of the universe is not made of the atoms we know. About a quarter is dark matter that interacts only through gravity. Nearly 3/4 is dark energy, a pressure that pushes space apart. The same constant that once tried to freeze the cosmos may now be responsible for its acceleration. The oldest light does not only tell us about the past, it guides our models of the future. A flat geometry means the universe will expand forever, slowing but never stopping unless dark energy changes. The density of matter tells us how fast galaxies will drift apart. The background acts like a clock whose ticks are written in temperature. Each degree, each fluctuation, is a record of cosmic time. The emotional weight of this discovery is hard to overstate. Every person who looks up at the night sky sees stars that differ in color and brightness. But beneath them, invisible to the eye, there is a uniform glow that belongs to all directions equally. It connects us to the first dawn. The light has crossed almost 14 billion years to reach our instruments. It has passed galaxies that no longer exist, absorbed and re-emitted countless times, yet its overall shape remains true. To touch it with an antenna is to touch history. Consider how small we are. A single photon from the background has been traveling since before the first atoms of our bodies existed. It passes through you without pause, a silent witness to everything that has happened since time became meaningful. Billions of them pass through every square centimeter each second. They are not dangerous. They are ancient. They are the steady heartbeat of the cosmos. Some wonder whether there might be other universes beyond this one, perhaps with different temperatures or different patterns in their oldest light. That question remains open. The background we can measure belongs to our own observable patch. It defines the limits of what we can see and test. Beyond that horizon, imagination takes over. But imagination without data is only myth. The microwave sky is where myth meets measurement. The practical work continues. New missions measure polarization, the subtle twisting of the light caused by gravitational waves from the earliest moments. These measurements might one day reveal how space itself began to expand faster than light during an early inflationary phase. If those patterns are confirmed, they will take us as close to the first instant as physics can reach. Until then, the background remains the gold standard for cosmology, a truth written not in words but in radiation. In plain terms, the oldest light is both fragile and eternal. It can be drowned by a cell phone tower, yet it has survived for nearly the entire history of the cosmos. It carries the same message to every receiver that listens carefully enough. It says the universe began hot, expanded, cooled, and left behind a perfect memory of that sequence. The message requires no translator, only patience. Why it matters once more is that this light closes the loop between theory and observation. The priest's prediction, the Redshift law, and the constant that failed all meet here. The glow on the sky confirms the expansion, measures its rate, and proves that the cosmos has aged. The background is the experiment the universe performed on itself, and we are only reading the results. When we stare at the color-coded maps from satellites, we are seeing not art, but arithmetic. Each pixel is a count of photons, each tone a fraction of a degree. The picture is beautiful because truth often is. It reveals that our vast universe began as a small, uniform field with the tiniest imperfections, and those imperfections became everything. The oldest light is our inheritance. It tells us that the universe is understandable, that time has direction, and that measurement is a form of faith in reality. No ancient story, no sacred text, no myth has ever left such a clear signature. The sky itself carries the proof, etched in radiation, waiting for eyes that know how to listen. We now move from the calm of that fossil light to a modern tension, where two clocks of the cosmos disagree about its pace, and the search for their harmony begins. Every expansion needs a rhythm. The universe has one too, a beat written into the relationship between distance and velocity. When we say the cosmos is expanding, we mean that the separation between galaxies grows over time. The rate of that growth is measured by a single number, the Hubble constant. It is the heartbeat of the universe, the measure of how fast now is compared with then. Yet, like two clocks that both claim accuracy, the universe seems to offer different answers when we measure it in different ways. The story begins with the first attempts to turn the redshift law into a precise value. By comparing the apparent brightness of galaxies with their color shifts, astronomers derived the slope of the expansion curve. Early numbers were wildly high, implying that the universe was younger than the oldest stars. As instruments improved, the estimates fell, then stabilized around 70 kilometers per second per megaparsec. That means every million parsecs of distance adds 70 kilometers per second to the speed of recession. It sounds precise, but the serenity of the number hides turmoil. Different methods give different slopes, and the gap between them refuses to close. In one approach, we look outward. The background radiation of the cosmos carries an imprint of how space expanded in its infancy. By fitting that pattern to our best models, we can predict how fast the universe should be expanding today. This method reads the cosmic past as a time capsule, using early light to infer the present. It gives one value for the Hubble constant. In another approach, we look inward, at nearby galaxies and exploding stars whose brightness we can calibrate directly. These act as standard candles, giving a local measure of expansion without relying on ancient light. The two methods, early and late, disagree by about 10%. The difference sounds small, but in cosmic terms, it is enormous. The tension has become a central puzzle of modern cosmology. If both sets of data are correct, then something fundamental is missing in our model. Perhaps the early universe contained an unknown ingredient that altered its rhythm. Perhaps light behaves differently across epochs. Perhaps our assumptions about the ladder of distances need refinement. Every option carries consequences, and none yet resolves the mismatch completely. In plain terms, it is as if we have two wristwatches that both keep perfect time, but drift apart when we compare them after a long journey. The difference is not enough to ruin the day, but enough to question the mechanism. One watch measures time by counting the swings of a pendulum, the other by the vibration of a crystal. Both are right within their own domains. The question is which domain describes the cosmos we inhabit. To make matters more vivid, imagine two lighthouses across an ocean. One flashes its beam according to an ancient schedule recorded in a logbook. The other flashes in real time as we watch. When we compare the pattern of flashes, we find that the ocean between them has stretched differently than expected. Did the water change, or did one lighthouse drift? The Hubble tension is that ocean's riddle. The data that favor the early light come from satellites that measured the cosmic microwave background. Those maps fix the parameters of the early universe so well that they predict the current expansion rate with high precision. The local measurements rely on a different chain, from pulsating stars to supernovae to galaxies. Each rung of that ladder carries its own uncertainties, but the accumulated precision is also impressive. Both communities have checked for bias, recalibrated, and reanalyzed. The gap remains. The universe is either expanding faster than the early light predicts, or the early light was subtly different from what we think. Why does this matter? Because it may be the first clear sign that our standard model of cosmology, successful as it is incomplete. A difference of 10% cannot be explained by small errors alone. Something in the physics, perhaps a new particle species, an early burst of dark energy, or a change in the strength of gravity over time, could bridge the gap. The Hubble tension has become a detective story, each clue pointing toward an unknown suspect. In everyday language, we are asking how fast the present moment moves away from the past. When we rewind the cosmic film, galaxies approach, light shortens, and temperature rises. The rate of expansion determines how long ago all the film frames meet. If that rate is higher, the universe is younger. If it is lower, the universe is older. Our answer to how fast is now decides the age of everything, including the stars we use as benchmarks. The disagreement also tests the integrity of observation itself. We often think of science as a smooth progression of refinement, but it is full of such moments where nature forces us to choose between cherished methods. In this case, both sides have passed every test they could invent. The instruments are different, the calibrations independent, yet the tension holds. It is as if the universe enjoys keeping one small secret, a reminder that knowledge is always provisional. Some physicists suggest that the tension could hint at exotic physics. Maybe the early universe experienced a brief acceleration beyond what we model, driven by an unknown field. Maybe light interacts with dark matter in subtle ways that change how we interpret distance. These ideas are speculative, but they keep curiosity alive. Others argue that we may have underestimated systematic uncertainties in the distance ladder, that tiny biases add up. Each possibility remains open, none yet dominant. Think of this in human terms. Two friends describe a shared memory. One recalls a slow, steady melody. The other swears it was faster. Both trust their senses. Both heard the same song. The truth may lie in how each defines tempo. The Hubble tension is our shared memory of time itself, contested by the tools we built to measure it. To approach resolution, new methods are emerging. Gravitational waves from colliding neutron stars act as standard sirens, providing distances without relying on light at all. By comparing the arrival time of waves and their electromagnetic echoes, we can measure cosmic expansion in an entirely new way. Early results are promising, but the uncertainty is still large. As instruments improve, these cosmic sirens may break the tie. Why it matters again is that the tension embodies the humility of science. Each side listens carefully to the data and adjusts the picture rather than forcing agreement. The conflict is not a crisis, but an opportunity, a pressure that pushes us toward better understanding. It is how every frontier in science begins. At its core, the question how fast is now is philosophical as well as physical. We define the present by what we can measure. In cosmology, that present spans billions of years. When we debate its rate of change, we are debating how to describe existence itself. A faster universe leaves less time for formation. A slower one offers more. Our place in the sequence depends on that rhythm. We have measured light that started its journey before life existed on Earth. We have tuned antennas to the afterglow of the primeval fire. Yet we still cannot agree on the pace of this moment. Perhaps that is fitting. The universe may be telling us that time is not a single melody, but a harmony of overlapping rhythms. On a human scale, the Hubble tension reminds us that disagreement is not failure. It is the friction that produces clarity. Every refinement of our cosmic clock deepens the story rather than ending it. Whether the true expansion rate is closer to the early light's prediction or to the local candles, the result will rewrite our understanding of cosmic history. If the early universe is faster than we think, new physics waits in the first few seconds of time. If the local measurements are right, the recent cosmos is livelier than our models allow. Either way, something new is hiding in plain sight. The answer is not beyond reach. It is in the numbers we already hold, waiting for the next generation of instruments to see what we have missed. The universe keeps time with a rhythm that is not ours, a pulse we can measure but not control. It is patient, persistent, and above all, precise. When we finally reconcile the two clocks, we will not only know the pace of now, we will know what hidden forces still guide the expansion. Next, we move from the rhythm of motion to the precision of design, where the constants of nature seem tuned with unsettling accuracy, and the question of why they fit so well begins to rise. The deeper we look into the fabric of the cosmos, the more the numbers seem to conspire. The constants that govern how stars burn, how atoms bond, and how gravity bends appear to rest within narrow margins. Change them even slightly, and the story of the universe collapses. This observation has come to be known as fine-tuning. It sounds mystical, but it is a technical statement about sensitivity. It says the equations that describe nature yield stable complexity only within a small range of values. Step outside that range, and chemistry, life, and even time as we know it would not unfold. Start with gravity. If its strength were just a little higher, stars would burn too quickly and collapse into black holes before planets could form. If it were weaker, gas clouds would never condense, and the sky would be dark forever. The same precision holds for the strong nuclear force that binds protons and neutrons. Increase it by a few percent, and hydrogen fuses too easily, leaving no long-lived stars. Decrease it, and atoms heavier than hydrogen would not exist. The periodic table would end before it began. Even the ratio of the proton's mass to the electron's mass must be close to what it is, or stable molecules would fail to form. In plain terms, the universe behaves like a vault whose lock opens only when every dial aligns. Each constant is a dial, and together they produce the conditions for structure and life. It does not mean the vault was built for us, only that we live in one of the rare configurations where the door happens to stand open. Whether that alignment is accident or intention remains an open question. Some find this precision unnerving. If the constants were set by chance, why do they sit so close to the edge of catastrophe yet allow beauty and complexity? If they were set by necessity, what deeper law fixes them? The problem runs deeper than philosophy. It touches the boundary between explanation and existence. Our best models, including quantum field theory and general relativity, treat these constants as given. They can be measured but not derived. The laws explain how the universe behaves, not why the parameters have those values. The list of sensitive quantities grows. The cosmological constant, the small term that drives accelerated expansion, is one of the most puzzling. Its measured value is tiny, but not zero, roughly 120 orders of magnitude smaller than naive theory predicts. If it were even a little larger, the universe would expand too fast for galaxies to form. If it were smaller or negative, everything would have collapsed long ago. That delicate balance is almost absurd. The equations allow a vast range, yet nature picked a number that seems unnaturally precise. In everyday language, the cosmos is a tightrope walker balancing on an invisible thread. Every step forward requires a correction of incredible precision, too much weight on one side, and the performer falls into a void or implodes into fire. The fact that we are here to watch implies that the balance held, at least for now. But the implication of our own existence cannot be used as proof that the universe was designed for it. It may simply mean that only in balanced worlds can observers arise to notice. The anthropic argument begins here. It states that we should not be surprised to find the constants compatible with life, because life could not exist to ask the question otherwise. This logic is circular but not meaningless. It reframes the mystery as selection rather than design. Among countless possible universes, we inhabit the one that allows thought. The others, sterile and silent, cannot complain about unfair odds. Whether such alternate universes actually exist is a matter of speculation. Yet the idea of a multiverse offers one natural way to dilute the improbability. If the cosmic lottery draws infinitely many tickets, at least one will win by necessity. Skeptics reply that invoking countless unseen universes to explain ours is extravagant. A theory that multiplies realities without evidence risks replacing one mystery with another. Perhaps the constants are fixed by a deeper symmetry not yet discovered. Perhaps the mathematics of higher dimensions constrains them the way the geometry of a sphere constrains the shape of lines drawn upon it. Until we know, the fine-tuning remains both a clue and a riddle. The human scale can help us think more clearly. Imagine a safe with dozens of dials. Each dial controls some parameter of physics: gravity, charge, mass, expansion rate. Most combinations keep the door sealed. Only a tiny subset opens it. We did not set the dials. We simply woke up inside the open vault. That does not prove a locksmith's hand. It shows that possibility and rarity can coexist. The surprise lies not in the door being open, but in our tendency to expect otherwise. Why does this matter? Because it connects cosmic numbers to human meaning. The realization that everything depends on fragile balances can lead to two responses: awe or despair. Awe, because we see how intricate the architecture is. Despair, because we may never know why it is so. Yet both reactions stem from the same insight that existence itself is improbable. The correct attitude is not submission to mystery, but gratitude for opportunity. The laws are what they are, and they allow us the privilege to ask why. In plain terms, fine-tuning is the study of what would break if the knobs of reality were turned. It teaches humility by showing how easily the whole machine could fail. When we simulate universes with different constants, most die young. They either collapse before they cool, or they expand into sterile thinness. Ours survives because its ingredients sit within a delicate window. This fragility is not weakness. It is the condition for complexity. From a scientific view, the challenge is to test these ideas. We cannot alter the constants, but we can measure how they manifest. We can look for variations in the fine structure constant over cosmic time. We can test whether dark energy truly remains constant or evolves. Each experiment probes whether our universe is as rigid as it seems or whether it allows slight drift. A small drift would be revolutionary. It would mean the dials are not fixed, that the vault's combination is changing slowly, perhaps with consequences we cannot yet imagine. Speculation aside, the fine-tuning problem serves as a mirror for our minds. We crave reasons. We find design in patterns and intent in order. The universe may not care for our comfort, but it does offer an invitation. Understand the rules, and you will understand your place. That invitation is ancient, written in starlight, and it does not depend on belief. On the emotional level, fine-tuning carries a quiet irony. We call the cosmos vast and indifferent, yet its parameters appear narrowly hospitable. The same precision that makes stars possible also makes them temporary. The same nuclear forces that build life eventually destroy it. Fragility and endurance are two sides of the same law. We exist between them, balanced on a brief plateau of stability, watching the night. Why it matters once more is that these delicate conditions tie every atom of our bodies to the scale of the universe. If gravity were weaker, no galaxies. If the electromagnetic force were stronger, no stable atoms. If the expansion rate were different, no time to form worlds. The constants link the infinite to the intimate. They make our existence a numerical echo of cosmic order. Fine-tuning does not prove design, but it does highlight dependence. The stars rely on the same equations that describe us. The boundary between luck and law remains uncertain. Some future theory may reveal that what looks fine-tuned was inevitable all along. Until then, we live in a universe that balances at the edge of possible, fragile yet enduring, precise yet unpredictable. Next, we follow that thread toward the deepest frontier, where gravity itself must join with quantum rules, and the search for one language to describe everything truly begins. Every theory has its territory. Quantum mechanics governs the small, the uncertain, and the fast. General relativity governs the large, the massive, and the slow. Each is complete within its realm, each experimentally flawless. Yet together they refuse to speak. When gravity meets the quantum world, their languages clash. The result is an unfinished map of reality, a coastline drawn in exquisite detail that suddenly breaks off into fog. In the quiet mathematics of relativity, space-time is a smooth fabric. Matter curves it, and curvature tells matter how to move. The geometry is continuous. Distances can be divided endlessly, but in the quantum view, the world is granular. Energy, light, and motion come in discrete steps, never in continuous flow. Combine those principles, and contradictions multiply. How can a smooth stage support actors that hop instead of glide? If we zoom in far enough, does space-time itself shimmer in quanta, or does the concept of space lose meaning altogether? The problem is not academic. In everyday physics, we can ignore the conflict because gravity is weak at small scales. A falling apple does not need quantum correction. But inside black holes or at the birth of the universe, gravity becomes intense enough to warp space into a single point, while quantum mechanics forbids perfect certainty. At that intersection, both theories collapse. Infinity appears, a warning that our equations are reaching beyond their license. Scientists have tried for decades to merge the two frameworks into one. The attempts fall into two broad families. The first begins with relativity and adds quantization, treating the gravitational field as another force with a particle carrier, the graviton. The second starts from quantum mechanics and builds space-time as an emergent property of information. Both approaches succeed in fragments, but neither yet unites the continents of theory. In plain terms, imagine two musical scores written for different instruments. One uses continuous tones of a cello, the other the percussive beats of a drum. Each is beautiful on its own. Play them together, and the rhythms clash to create harmony. We need a new composition, not a compromise. The search for that harmony is the quest for quantum gravity. String theory offered one vision. It replaces point particles with vibrating strings so tiny that even the most powerful microscope could not see them. Each vibration mode corresponds to a particle, and one of those modes behaves like a graviton. The theory elegantly includes gravity and quantum mechanics under one roof, but it demands extra dimensions beyond the familiar four and allows countless possible universes, each with its own set of constants. The beauty is undeniable. The testability remains thin. Without evidence, the grand harmony risks sounding like imagination. Another path is loop quantum gravity, which treats space itself as woven from finite loops, a network of relations that quantize area and volume. According to this picture, space-time is made of discrete atoms of geometry. At scales far larger than these loops, the fabric appears smooth, just as a cloth looks continuous from afar. This approach predicts that singularities might dissolve into finite, bouncing cores, removing the infinities that plague classical theory. Yet experiments to verify this remain beyond reach. Why does this matter? Because the tension between quantum mechanics and relativity defines the edge of human understanding. Every black hole, every early moment of the universe, every particle interaction at extreme energy points us toward the missing union. Without it, we cannot fully explain how information behaves when trapped by gravity, or how time itself emerges from deeper principles. At the heart of the conflict lies the concept of information. Quantum mechanics says information is never destroyed, only transformed. Relativity, through black holes, seems to contradict this. If matter falls into a black hole and the hole evaporates through radiation, where does the information go? The paradox gnaws at the foundation of both theories. Hawking radiation, predicted by combining quantum effects with curved spacetime, offered a clue: black holes are not eternal. They radiate energy and shrink. But whether the lost information escapes or vanishes remains uncertain. The answer could reveal the quantum nature of space-time itself. In everyday language, the question is whether the universe keeps perfect records. If it does, then nothing is ever truly erased. If it does not, then our physics admits irreversible loss. The first choice preserves order, the second rewrites it. The debate continues, fueled by equations, simulations, and the stubborn silence of observation. Think of the map we have of the cosmos as a globe missing its poles. Between the quantum and the cosmic, there is a gap like an uncharted ocean. We can sail around its edges, describing the coasts of atoms and galaxies. But the deep center remains unexplored. The goal is not just curiosity. Every technology built on quantum mechanics or relativity works because those theories are stable, but their disagreement hints at limits to stability itself. Understanding where the map ends tells us where new physics must begin. Some researchers look to the holographic principle, a strange idea that space-time volume might be encoded on a lower dimensional boundary. According to this principle, the universe behaves like a projection, with information written on its surface the way data are stored on a disk. This notion has explained certain puzzles about black holes, showing that their entropy is proportional to surface area, not volume. If true, the holographic view might mean that gravity and geometry are emergent phenomena, born from the entanglement of quantum bits. Why it matters again is that these attempts transform our understanding of reality, from substance to relation. Instead of thinking of space as an empty container, we begin to see it as a web of interactions, a network that gives rise to distance and time. Matter becomes geometry condensed, and geometry becomes information in motion. This reframing dissolves the ancient boundary between what is physical and what is abstract. In plain terms, if gravity and quantum rules can be united, the universe will no longer be a patchwork of approximations. It will be a single tapestry where the smallest vibrations of energy also describe the largest curvature of space. Such a theory could explain the birth of the cosmos, predict what happens beyond the event horizon of black holes, and perhaps reveal whether space itself has a smallest possible unit. The challenge is immense. Our best experiments can barely test gravity at microscopic scales. Particle accelerators reach energies far below the level where quantum gravity would dominate. Cosmology offers indirect clues, but interpreting them requires assumptions we cannot yet verify. We are explorers reading reflections in waves, not the seabed itself. Yet the pursuit continues because the stakes are high. Unifying gravity and quantum mechanics is not just a theoretical ambition, it is a search for coherence. Two perfect languages describing one reality must, at some level, agree. The human mind resists accepting two contradictory truths. So we build new mathematics, new detectors, new metaphors, chasing the line where they meet. On a human scale, this search mirrors our own divided nature. We too live between two regimes, the measurable and the mysterious, the continuous and the discrete. Our daily lives follow classical order, but our thoughts, emotions, and discoveries leap in quantum steps. The need to reconcile opposites is both physical and psychological. The unfinished map reminds us that ignorance is not failure. Every frontier once looked impossible until the right instrument appeared. The telescope joined light with geometry. The spectrograph joined chemistry with stars. And perhaps one day, a quantum sensor will join gravity with uncertainty. When that happens, the map will extend further, and the fog will retreat a little more. For now, we live with two truths that do not yet converge. Relativity paints the grand curvature of existence. Quantum theory describes its fine grain. Between them lies a silence that may hold the next revelation, the day that silence speaks. The oldest paradoxes of time and space will find their answer. We continue next to the question that all these efforts point toward, whether the universe ends in cooling darkness, collapses in fire, or cycles through eternal rebirth. Every question about the beginning eventually turns toward the end. If the universe had a first moment, will it also have a last? The equations that describe cosmic expansion do not stop at the present. They can be extended forward to forecast the possible futures of everything. Those futures depend on a delicate balance among gravity, energy, and the invisible pressure that drives the widening of space. Each term in that balance decides whether the story fades, rebounds, or continues without end. At first, astronomers assumed that gravity would slow expansion. The logic was simple. Everything pulls on everything else. Over enough time, the pull might stop the outward rush and reverse it, leading to a future collapse. This scenario became known as the Big Crunch, the mirror image of the Big Bang. In that picture, galaxies would draw closer, stars would collide, and temperatures would soar until matter itself broke down. Space would fold back upon itself, and time might reach a natural stop. But when the evidence for acceleration appeared, the prospect of a crunch began to dim. The discovery of cosmic acceleration replaced the simple picture with something stranger. A mysterious form of energy, called dark energy, appears to fill all of space and push it outward. If this energy remains constant, expansion will continue forever. Galaxies now bound together will remain local, but the rest of the universe will slip beyond the horizon of visibility. Over time, starlight will fade, new stars will stop forming, and the sky will empty. The universe would not die in fire, but in solitude, a slow dimming into heat death. In plain terms, a heat death is not an explosion or a freeze. It is the exhaustion of difference. Every gradient that allows work, temperature, motion, radiation, eventually equalizes. Energy spreads until nothing can happen because everything has already happened. Stars burn their last fuel. Black holes evaporate. And even the background radiation cools toward absolute zero. The cosmos becomes uniform again, as it was at the start, but without the potential to change. There is another possibility. Dark energy might not be constant. If it grows stronger with time, it could tear space apart. This is the scenario known as the Big Rip. Galaxies would first drift away from one another, then solar systems, then planets from their stars. At the extreme, even atoms would separate as the expansion rate exceeded every binding force. Time itself would lose coherence in a final disintegration. The rip is not poetic metaphor. It follows directly from equations if the energy density rises faster than space can compensate. Yet we do not know if this will happen, because we do not yet know what dark energy truly is. Some theories imagine the opposite, that the acceleration may one day reverse. In those models, dark energy might decay or even switch sign, turning repulsion into attraction. The universe would slow, stop, and fall back upon itself. The collapse would heat matter until it ionized, then vaporized. Density would grow without limit, setting the stage for another burst of expansion, a cosmic bounce. The cycle would repeat, eternally alternating between growth and contraction. Each cycle might erase the memory of the last, or preserve faint traces, like scars in a fabric reused. The bounce idea offers philosophical comfort. It avoids the problem of a beginning or an end by replacing both with rhythm. In everyday language, the universe breathes. It inhales and exhales on scales of billions of years. No singularity, no absolute creation, just a cosmic heartbeat that never stops. But this view, appealing as it is, faces its own difficulties. The physics that could make space rebound at such densities remains speculative. The evidence, for now, leans toward one long expansion. Why does this matter? Because each possible fate reframes what it means to exist in time. If everything ends in a fade, meaning must be found in the present moment. If everything cycles, meaning lies in continuity, in the repetition of pattern. If a rip or a crunch awaits, then the universe is finite but dramatic, a story with a clear conclusion. The end is not just an astrophysical prediction. It is a mirror for how we measure value in a transient world. In plain terms, the cosmos offers three kinds of death: the quiet fade, the violent collapse, and the rhythmic rebirth. Each is consistent with our equations under different assumptions. The only way to know which one will happen is to measure the expansion rate and its change with precision. Future observatories are designed for that purpose. By mapping distant supernovae and gravitational waves, they will test whether dark energy remains steady or shifts. The fate of the whole depends on those decimal points. On the human scale, these distant destinies seem abstract. Yet they touch everything we do. The atoms that make up our bodies were forged in stars that will one day die. The stars themselves live within galaxies that will one day drift beyond each other's sight. Even in a forever expanding universe, islands of matter will remain bound for trillions of years before decay wins. The long future is cold, but not meaningless. It is a canvas of endurance, where entropy does not erase wonder but preserves it in the act of understanding. Why it matters again is that every scenario forces us to confront the limits of prediction. We can calculate the past with confidence because light carries its record to us. The future, however, must be extrapolated. The further we extend the line, the greater the uncertainty. Our equations are precise, but our knowledge of the ingredients is incomplete. The fate of all things may hinge on something we have not yet discovered, some hidden term that changes the outcome in the final act. The speculative edge grows sharper when we add quantum effects. Even if the universe were to approach heat death, quantum fluctuations could eventually produce new patches of space that inflate into separate universes. In that picture, creation never stops. It only migrates. Old universes fade. New ones ignite, each with its own constants and laws. Eternity, in this sense, is not endless life, but endless renewal. The cosmos becomes a field of potential, forever blooming in quiet cycles beyond our horizon. The idea of a multiverse stretches the mind but fits the math. Inflation, the rapid early expansion that shaped our visible universe, might still be happening elsewhere. Our cosmos could be one bubble among countless others, each isolated by distance and time. Some bubbles collapse quickly, others expand endlessly. The whole becomes a vast, self-generating landscape. We cannot see beyond our bubble, but its very uniformity hints at this larger process. The seeds of forever may already exist, hidden beyond measurable light. In everyday language, imagine a forest of universes, each a tree growing from the same soil of possibility. We live on one branch, watching the others through fog. Some trees fall and rot, some stand tall. The forest itself never ends. Whether this picture is true or poetic, it captures the feeling that the cosmos might be both finite in part and infinite in whole. The choice between bounce, fade, or forever may itself be false, because the universe could do all three in different corners of an unobservable expanse. Whatever the truth, the study of cosmic fate teaches humility. We have moved from myths of fire and flood to equations of curvature and density. Yet our questions remain the same. How long will it last? What came before? Will there be another after? The answers change. But the longing behind them does not. That longing is the signature of a conscious species within a vast, indifferent system, seeking meaning in a story whose end it will never see. The data we gather now will echo for generations. Each refined measurement of expansion, each map of distant galaxies, adds a brushstroke to the portrait of tomorrow. The final picture may be bleak or glorious, but its creation is our inheritance. We are the first creatures to measure the heartbeat of the universe, to compare its pulse with the passage of our own time. The future of the whole is not a prophecy, it is a mirror of curiosity. When we ask whether the universe will bounce, fade, or last forever, we are also asking whether knowledge itself can outlive its makers. Our observations, stored in light and memory, are already traveling outward, joining the background glow, long after the last star burns out. Those signals may still whisper across the void, proof that at least once, a a small civilization tried to understand the entire stage. Why it matters one final time is that each fate, no matter how cold or distant, becomes meaningful through awareness. The universe may not promise survival, but it offers comprehension. To know is to participate, even briefly, in the grand equation. The equations may end, the curiosity will not. We now leave the domain of measurement and step into reflection, where the question shifts from what the universe does to what it means for those who have learned to ask. Every measurement we have made has told us something about distance, time, and structure. But behind those numbers lies a quieter question, one that science cannot erase. What does it mean to live in a universe that has measured its own beginning? We stand surrounded by data that stretch backward 14 billion years, by light that left its source before Earth existed. Our telescopes look outward and backward at once. Each image is both a photograph of the past and a mirror of human curiosity. In the glow of those distant fires, we begin to see ourselves. For centuries, we imagined the universe as a stage built for us. Now we know that the stage is older, larger, and more indifferent than any myth allowed. Yet the more we discover its vastness, the more the human mind expands to match it. We have learned to think on scales that once belonged only to gods. A single thought today can reach across billions of light years, can model the collapse of stars or the birth of space itself. That capacity is our quiet defiance of insignificance. The universe may not care, but we do, and that caring changes everything. The tension between comprehension and humility is the essence of modern cosmology. We know we are small, yet we continue to measure the infinite. We know that our tools are temporary, yet we build them anyway, knowing they will outlast us. Each satellite, each telescope, each line of code becomes an extension of human senses into the deep cold beyond. It is not arrogance. It is gratitude made visible. We explore because the universe allows it. In plain terms, what this means is that our quest for knowledge is not separate from the cosmos. It is the cosmos becoming self-aware through us. We are one of its many experiments in reflection. Matter that once burned in stars now arranges itself into eyes and questions. The act of asking why the universe exists is the universe asking about itself. And that feedback loop may be the rarest phenomenon of all. When we look at the evidence, we see that everything began simple and became complex. Hydrogen became stars, stars became carbon, carbon became cells, and cells became minds. At each step, complexity required instability. Perfection does not grow. It stagnates. The universe has always advanced by imbalance, by fluctuation, by fine-tuned chaos. That truth is both terrifying and beautiful. It means that the fragility we observe in nature is not a flaw, but the engine of creation. Why does this matter? Because every fragile balance we find among the constants, every tension between theories, and every unanswered question about the future echoes within our own lives. We too are fine-tuned, temporary arrangements of matter holding back entropy for a while. We too live between collapse and expansion, between gravity and freedom. To study the cosmos is to study the conditions of our own consciousness. In everyday language, the story of the universe is also the story of attention. It begins scattered and ends focused. In the beginning, energy diffused in all directions, without structure. Then, through countless interactions, order appeared: galaxies, planets, living things, and minds that could notice. Attention is the local reversal of chaos, a small region where matter chooses to look back. Every question we ask is a lens focusing that ancient fire into meaning. If the universe will end in silence, does meaning vanish with it? The laws of thermodynamics seem to say yes, all differences fade, all motion ceases. But the act of understanding may carry its own permanence. Information, once created, cannot be entirely destroyed, only transformed. Our observations, encoded in light, in memory, and in the arrangement of matter, already travel outward, joining the background radiation, long after we are gone. Faint traces of our existence will drift among the stars, like dust illuminated by a dying sun. Think of this on the scale of a single human life. We live, we burn bright, we cool, and we leave traces, words, ideas, changes in others. The pattern repeats at every level. Stars write their stories in elements, galaxies in structure, humans in thought. In all cases, the message persists longer than the messenger. That persistence is not eternal in the literal sense, but it is long enough for meaning to echo. The echo may be faint, but it exists. Some people find comfort in the idea that consciousness is a cosmic accident. Others find despair. Both reactions miss the larger point: accident or design. The result is the same awareness exists. The fact that blind laws can give rise to eyes that look back at those laws is wonder enough. If the universe is a grand equation, then consciousness is its solution. The answer may not simplify the equation, but it completes it. Science gives us no promise of cosmic purpose. It offers process, not prophecy. Yet process itself carries grace. The universe is not meaningful because it was built for meaning. It becomes meaningful because minds within it make meaning. We find patterns, and by finding them, we extend the structure of understanding. Our search adds a new layer to the universe's complexity. A recursive fold where matter considers itself. That may be the only immortality that nature allows. In plain terms, the cosmos is not telling a story to us. It is telling a story through us. The atoms in our brains were once part of stars. Those stars were once part of the first luminous clouds born from hydrogen's simplicity. When we speak of the early universe, we speak of our own ancestry. When we trace redshifts or background radiation, we are reading the family album of existence. The connection is not poetic metaphor, it is literal physics. Why it matters again is that knowing this changes how we live. The knowledge of impermanence need not diminish value. It deepens it. When we accept that the universe does not owe us meaning, we become free to create it ourselves. The fragile balances that sustain life become sacred not by decree, but by recognition. To understand their rarity is to feel reverence, even without religion. Every discovery in cosmology adds both clarity and mystery. We now know the age of the universe, the shape of its expansion, the origin of its light. Yet each answer opens a deeper question. Why are the laws as they are? Why should something exist rather than nothing? What, if anything, breathes fire into the equations? Science cannot close those questions. It can only refine them. Perhaps that is the point. Perhaps endless questioning is the natural state of an aware universe. The philosopher in us must coexist with the scientist. Data without reflection is sterile. Reflection without data is fantasy. Together they form a loop, one feeding the other. As observation becomes meaning and meaning guides observation. This loop is our version of cosmic balance, our way of bridging the finite and the infinite. It mirrors the interplay between matter and energy, order and chaos, gravity and expansion. Knowledge and wonder are two sides of the same universe. On a human scale, the story offers perspective. Our lives are shorter than a spark on the timeline of the cosmos, yet that spark carries the full light of comprehension. We may never travel to distant galaxies, but we have already reached them in thought. We may never witness the universe's end, but we can predict its outline. To imagine that future is to participate in it. To measure is to connect. Some might say that the universe is indifferent, that it will proceed unchanged whether we exist or not. That may be true physically, but not conceptually. A universe without observers has no description, no self-awareness, no questions. Observation gives it context. The act of noticing transforms mere existence into history. Our small consciousnesses are the instruments through which the universe perceives itself. That may not change its fate, but it changes its meaning. As the cosmic story continues beyond our reach, we are left with the quiet truth that knowing is itself a kind of creation. Understanding rearranges reality within the boundaries of mind. Each insight is a new alignment of matter and thought, a brief structure against entropy. When we seek knowledge, we are not resisting the universe. We are echoing its original drive to unfold. A line from ancient wisdom once said that to study nature is to study the divine. Today, we might rephrase it: to study the cosmos is to witness self-reference made real. The universe creates observers that can describe it. Those descriptions loop back, influencing how future observers will see. This recursion is not supernatural. It is the natural consequence of evolution and memory. Yet it feels sacred, because it is intimate. The infinite has touched the finite, and the finite has learned to speak. At the end of this long journey, what remains is not certainty, but connection, the constant that would not hold, the galaxies that flee, the afterglow that fills the sky, the numbers that balance on the edge of collapse, all lead back to the same realization: we are part of the process. We are fragments of the same expansion that carries the stars apart. The universe is not something we watch from outside. It is something we are inside, something that watches itself through us. So the question changes. No longer what will happen to the universe, but what will the universe become through us? The difference is subtle but profound. The first question seeks prediction. The second invites participation. The cosmos may fade, bounce, or last forever, but the act of knowing ensures that none of it is wasted. Awareness itself is the quiet flame that outshines time. If the universe can look back through our eyes, what new question will it ask next?